Okay, let's unpack this. We've all seen the headlines. It is probably the most famous, scary story in the entire canon of astronomy. You open a science magazine, you click on a YouTube video, and there it is. The inevitable, cataclysmic, head-on collision between our own Milky Way galaxy and our massive neighbor, Andromeda.
It's the ultimate cosmic fender bender for sure.
Exactly. And the numbers are usually just absolutely terrifying. We're talking about two colossal islands of stars rushing toward each other at, what is it, 110 kilometers per second?
Roughly that, yes.
Yeah.
About 110 kilometers per second. I mean, that is fast enough to travel from New York to London in under a minute.
Right. And the standard story goes that in about, 4 or 5 billion years, bam, we merge. The sky lights up, chaos ensues. But here is where it gets really interesting and why we are doing this deep dive today. While we are all worrying about the stars colliding, which, spoiler alert, we will get to, and it's not what you think, the real drama, the actual main event, isn't happening out in the spiral arms. It's happening right in the dead center.
That's right. Because the stars are just the audience. The main characters here are the monsters hiding in the middle, the supermassive black holes.
And this is where the story gets so much more complicated. Because as it turns out, getting two galaxies to smash together is the easy part. Getting their black holes to actually merge,
Right.
that is a theoretical nightmare that has kept astrophysicists up at night for decades. It's called the final parsec problem.
Oh, it is one of the most stubborn paradoxes in galactic dynamics. Theory says they should stall. Reality, observation says they merge. So we have to figure out what we are missing in the theory.
And that is our mission today. We're going to dig into a stack of sources that ranges from the latest astronomical data to a really dense, fascinating doctoral dissertation by Fazil Mahmoud Khan from the University of Heidelberg. We're going to trace the life cycle of this collision from the first approach to the final chirp of gravity waves.
And we're going to see how the very shape of the galaxy, literally, whether it looks like a frisbee or a football, might be the secret key.
The key to saving these black holes from being frozen in place forever. It's a journey from the scale of millions of light years down to a single city-sized event horizon.
It really is.
So let's start with the big picture. The collision itself. I mentioned the standard story, 4 billion years, inevitable doom. But looking at the sources, specifically the recent updates from 2025, that inevitable part might be a bit shaky.
It is fascinating how science evolves on this. For a long time, based on Hubble data from around, I think, 2012, we were sure.
Wow.
The vector was locked in. Andromeda is coming right for us.
That was the consensus.
Absolutely. But the newer data, specifically from the Gaia spacecraft and updated Hubble observations, has thrown a real wrench in the gears.
This is the study by Tilsawala and colleagues, right?
Exactly. When you factor in the gravitational chaos caused by the Large Magellanic Cloud and the Triangulum Galaxy, which are also major players in our local group, the math it changes. It turns out we can't just look at the Milky Way and Andromeda in isolation. It's a 3 or 4 body problem.
Right, which is notoriously difficult to solve.
Impossible, really, without massive simulations. And the latest probability, it's about 50-50.
50-50. So there is a coin flip's chance that we just miss.
In the next 10 billion years, yes, there is a roughly 50% chance they won't collide at all in that time frame. They might just swing past each other, do a little gravitational dance. So the certainty we used to scare school children with is actually a statistical toss-up.
That is wild. We might just wave at them as they fly by. But for the sake of this deep dive, and because it's way more fun, let's assume the standard model holds. Let's assume we do hit. What does that actually look like?
Well, if they hit, they don't just bounce off. Gravity is relentless. They will pass through each other, stretch out into these long tidal tails, and then gravity pulls them back together.
So it's not one collision, it's a series of passes.
A series of passes, exactly, over hundreds of millions of years until they eventually settle down and form a single massive galaxy. The nickname for this future abomination is Milkomeda.
Or Milkdromeda, I've seen that too.
Yes, both work.
Milkomeda. Sounds like a candy bar, but I'm guessing it's less sweet and more destructive. Or is it? This brings us to the empty space paradox. I think this is the thing that trips people up the most. Two galaxies collide. That means stars crashing into stars, planets smashing into planets, right?
You would absolutely think so. But this is where human intuition just fails us when it comes to scale. Galaxies are not solid objects. They're essentially ghosts made of gravity and light.
A ghost made of That's a good way to put it.
The sources use a great analogy here. Imagine the sun is a ping pong ball.
Okay, I've got a ping pong ball in my hand.
Now, at that scale, where's the next nearest star, Proxima Centauri?
Down the street? Across town, maybe?
It's a P about 1,100 kilometers away.
Whoa, wait, a ping pong ball here and a P in, like, Chicago.
Exactly. And the galaxy is just billions of these ping pong balls in P separated by thousands of kilometers of pure nothingness. So when you throw two galaxies at each other, the probability of two stars actually physically colliding like billiard balls is negligible.
So it's not zero, but
It's effectively zero. You're more likely to win the lottery every day for a year.
So the solar system isn't going to get T-boned by some alien sun.
No. The sky will change dramatically. The night will get much brighter with all these new stars, but physically, we're fine.
Well, I mean, assuming the sun hasn't boiled the Earth dry by then, which it will have, but that's a different problem.
Right. Small comfort for our distant descendants. But if the stars don't hit, why do we call it a violent event? What actually happens to the galaxy if the things inside it don't touch?
It's not a violence of impact, it's a violence of orbit. This is what we call violent relaxation.
Violent relaxation? That sounds like a terrible spa treatment.
It effectively is for the stars. Right now, the stars in the Milky Way are orderly. They move in a nice flat disk like cars on a racetrack. Everyone's going in the same direction.
Right, very organized.
But when Andromeda comes barreling in, the gravitational potential, the landscape of gravity itself changes rapidly. It fluctuates wildly. It's like the racetrack is suddenly buckling and twisting under you.
So the track disappears. The track disappears, the road map is torn up and thrown away, the stars lose the memory of where they were, their ordered motion transforms into random energy, they get scattered into these random chaotic orbits.
And that's what puffs up the galaxy.
That's exactly it. The beautiful spiral arms are completely destroyed, the disk is puffed up, and you end up with a giant amorphous blob of stars. That's why Melcometa will likely be an elliptical galaxy, just a big football-shaped swarm of stars with no discernible structure.
Okay, so the stage is set. We have Melcometa. It's a mess. The stars are scrambling. But deep inside this mess, we have the two heavyweights. Sagittarius A, our black hole, what is it, about 4 million times the mass of the sun?
Around 4 million, yes. A respectable size.
And then the Andromeda black hole, which is a beast.
Oh, much bigger. Estimates vary, but it's likely around 100 million solar masses. Maybe even more.
So we have a featherweight and a heavyweight. And this is where the dissertation by Fazil Mahmoud Khan really becomes our guide. We need to get these two black holes from thousands of light years apart down to zero. Khan breaks this down into 3 phases. Let's walk through them. Phase 1, the descent. How do they find each other in this mess?
This is where we meet a force called dynamical friction.
Dynamical friction. It sounds like regular friction, like tires on a road, but for space.
That's the idea, but remember, there's no air, no road. This is gravitational friction. Imagine the supermassive black hole as a heavy boat moving through a sea of water, but the water is made of stars.
Okay, a boat in a sea of stars. I can picture that.
As the massive black hole moves forward, its gravity pulls on the stars around it. It deflects them. But because it's moving, by the time the stars fall toward where it was, the black hole has moved on. So you get a concentration of stars, a wake, building up behind the black hole.
I see. So there's a clump of stars trailing behind it, like the wake behind a boat.
Exactly. And that clump has its own gravity, so it pulls backward on the black hole. It acts like a drag force. It slows the black hole down.
And because the black hole loses energy, it sinks.
It sinks. It falls deeper and deeper into the gravitational well toward the center of the new galaxy. This drag is calculated using the Chandrasekhar formula, which has this thing called the Coulomb logarithm in it.
I remember seeing that in the text. It's
Yep.
about the ratio of distances, right?
Precisely. It's the ratio of the maximum to the minimum impact parameters. Basically, it's a way of quantifying how far out the black hole's influence extends.
So it's surfing down a wave of its own making, essentially.
That is a poetic way to put it, and this process is very efficient. Kahn's work highlights that in major mergers, the black holes don't just fall in naked. They stay buried in the centers of their original galaxies, their cusps, these dense clusters of stars, for a long time.
Oh, so they bring their own little posse with them?
They do, and these dense clusters of stars act like extra weight, making the friction even stronger. They sink faster because they are heavier, effectively.
So they drag their entourage with them, and that helps them sink. Okay, so dynamical friction brings them together. They sink to the middle of Melcometa. Now they are close. We are entering phase 2. This is where things get sticky.
Right. Very sticky. They get to within a few light years of each other. At this point, they become gravitationally bound. They are now a binary system. They are orbiting each other,
A death spiral.
ideally. But here, dynamical friction stops working.
Why? The sea of stars is still there, isn't it?
It is, but the physics changes. The black holes are now moving relatively fast around each other, and they're in a very small region. They've basically cleared out their immediate neighborhood. They're no longer interacting with the broad background of the galaxy in the same way. The interaction goes from being fluid-like to granular.
Granular, meaning one star at a time.
Exactly. It becomes a three-body problem, the two black holes plus a star.
And this is the gravitational slingshot.
Correct. A star from the galaxy wanders a bit too close to the binary black holes. The combined gravity of the binary grabs the star and flings it out at an incredibly high speed.
Like a kid kicking a rock.
Yes, but with conservation of energy. If the binary gives the star a huge kick, adds a ton of kinetic energy to the star, the binary must lose that energy.
And when it loses energy,
Its orbit shrinks. The black holes get closer. This is called hardening the binary. It gets tighter and harder to break apart.
so they're using the stars as fuel, basically.
Yeah.
Ejecting stars to pay for their ticket inward.
Precisely. And this leads us directly to the crisis, the final parsec problem.
The name sounds like a thriller movie. The Final Parsec.
It is a thriller for theorists, I promise you. Here is the issue. To keep shrinking, the binary needs a constant supply of stars to slingshot. It needs fuel. But the binary is very, very efficient. It creates something called a loss cone.
Let's define that. The loss cone.
Imagine a specific zone of orbits, a set of trajectories that pass close enough to the black holes to get ejected. That is the loss cone. The binary eats through the stars in that cone very, very quickly. It kicks them all out.
So it empties the tank.
It empties the tank completely, and once those stars are gone, there is nothing left to interact with. In the classic theoretical models, specifically, models that assume the new galaxy is a perfect sphere, there is no easy way to refill the tank.
Why does being a sphere matter so much?
Because in a perfect sphere, orbits are very regular. They're repetitive, like grooves on a record. If a star isn't already on a path to hit the center, it won't naturally change its path to go there.
Angular momentum is conserved too strictly.
Exactly. The symmetry is too high. So the stars in the safe zone stay safe. The stars in the danger zone are ejected. The binary sits in an empty hole it has carved out, completely isolated.
It stalls.
It stalls at a separation of about 1 parsec, roughly 3.26 light years.
That's tantalizingly close in galactic terms,
Mhm.
but too far to merge.
Way too far. At 1 parsec, they aren't losing energy to friction anymore, and they are much too far apart for gravitational waves to kick in and take over. They would just orbit each other forever, or at least for a timescale longer than the age of the universe.
Which would mean we should see binary supermassive black holes everywhere, just stuck in limbo. But we don't, do we?
We don't. We see hints of them, but not nearly enough to suggest this is a common dead end. And we know mergers happen because we see the aftermath, these gigantic black holes in the centers of giant elliptical galaxies. So the spherical model must be wrong.
Enter Fazil Mahmoud Khan and the messy galaxy solution.
Exactly. This is the core of the dissertation. Kahn's work attacks this problem by challenging the fundamental assumption of the sphere. He uses n-body simulations. These are massive computer programs that calculate the gravity of millions of individual particles to show what really happens in a merger.
And the headline finding: real galaxies aren't spheres.
No, they are ugly, they are distorted. When two galaxies smash together, especially two disk galaxies, the resulting blob is triaxial.
Triaxial, meaning it has 3 unequal axes, like a flattened football or a bar of soap.
A squashed, stretched football is a great way to think about it. And this shape changes everything. In a spherical potential, gravity pulls you generally toward the center in a very predictable way. In a triaxial potential, the gravity is lopsided. It's asymmetric. It pulls harder in some directions than others.
And what does that do to the star's orbits?
It creates chaos. And in this context, chaos is our savior.
I love that. Chaos is the hero of the story.
It truly is. In a triaxial galaxy, you get orbital families that just don't exist in a sphere. Things like box orbits or pyramid orbits. But most importantly, you get these centrophilic orbits.
A centrophilic, meaning center-loving.
Exactly. These are orbits that don't stay in a lane. They wander. A star might start far out, but because of the lopsided, torquing gravity, its orbit twists and turns and precesses, and eventually it dives right through the center. It has no choice.
So the tank refills itself.
The tank refilling becomes a conveyor belt. The triaxial shape constantly funnels new stars from all over the galaxy into the lost cone. The binary never runs out of fuel. It can keep slingshotting stars, keep shrinking, and bridge that gap of the final parsec.
So the messiness of the merger is what allows the black holes to merge. If the universe were perfect and spherical, nothing would ever get done.
That is a profound truth in astrophysics. Symmetry is beautiful, but broken symmetry drives evolution. And Kahn's simulations prove this decisively. He ran these huge experiments on supercomputers, things like GRAPE clusters and later GPUs on clusters named Titan and Kulob.
And he compared the spherical models directly to the merger models, right?
Yes. And this is where he tackles that independence issue. Right, let's talk about that. Because reading the source material, it seems like this wasn't easy to prove.
No, it's a bit technical, but it's crucial for the validity of the science. In the old simulations of spherical galaxies, the rate at which the black holes merged depended on n the number of particles in the simulation. So if you ran the simulation with 100,000 stars, you got one result. If you ran it with 1,000,000, you got a different result.
Exactly. And that's a huge red flag. It means your result is a numerical artifact, not real physics. It means the refilling of the lost cone was just happening because of numerical noise, two-body relaxation that was exaggerated by having too few particles. If you extrapolated to a real galaxy with billions of stars, the process would grind to a halt.
So the old models were basically cheating, unknowingly.
In a way, yes, but Kahn found something completely different with the triaxial merger remnants.
What did he find?
He found that the hardening rate was n-independent. Whether he used a low-resolution simulation or a super high-resolution one, the black hole sank at the same speed. This proved that the mechanism wasn't numerical noise, it was the geometry of the galaxy itself, the triaxiality that was driving the merger. It was a real physical effect.
That is the smoking gun.
Yeah.
Geometry saves the day. Now, Kahn's dissertation goes into some specific case studies. It's not just one type of merger, is it?
No, he looked at several scenarios, which is what makes the work so robust. The most efficient one, as you might guess, is the equal mass merger, when two galaxies of roughly the same size hit each other.
Like Milky Way and Andromeda. They are comparable, aren't they?
Andromeda is a bit bigger, but yes, it's considered a major merger, maybe a 1:3 or 1:4 mass ratio. In these cases, the collision is so violent, it creates a very strong triaxial shape. The football is very distorted.
And that drives a faster conveyor belt.
A massive one. He found the binary hardening rates were about 5 times higher than even the most optimistic spherical models. Coalescence, the final merger, happens incredibly fast, less than 1 billion years after the binary forms.
That's quick on cosmic timescales. But what about when a tiny galaxy hits a big one? A minor merger. Galactic cannibalism.
That is chapter 8 of the dissertation, and this is where it gets tricky. He investigated different mass ratios, Q as they call it. If the incoming galaxy is too small, say less than a 20th of the mass, a 1:20 ratio or less, it doesn't have enough punch to really distort the big galaxy.
So the big galaxy stays mostly spherical.
Exactly. It gets a little shaken up, but not enough to create that strong triaxial shape.
So the stalling problem comes back.
It threatens to. It really does. But Kahn found another twist. Eccentricity.
The shape of the binary's orbit itself.
Right. In these unequal mergers, especially if the colliding galaxies have shallow density profiles like disk galaxies do, the black holes tend to fall into very eccentric, elongated orbits. They don't circle each other in perfect rings. They dive at each other in these long elliptical loops with an eccentricity E of like 0.9.
So they get very close, then very far, then very close again. And how does that help?
An eccentric orbit brings them very close together at the periapsis, the closest point of approach, much sooner than a circular orbit would. And when they get that close, they can start to emit gravitational waves much earlier. It shortcuts the process.
So it's like they're skipping the slow stellar slingshot phase and jumping ahead to the final gravitational wave phase.
It helps them bridge that gap. So even in many minor mergers, they usually find a way to merge, though it might take a bit longer. Nature finds a way.
It's amazing. There are all these backup mechanisms. Now, I want to pivot to something that I found really visual in the reading. We talked about the black holes kicking stars out, slingshotting them. Kahn mentions that this happens on a truly massive scale.
It is absolutely massive. To merge, the binary has to shed a lot of energy and angular momentum. It transfers that to the stars. The simulations show that to get from a parsec down to the gravitational wave regime, the black holes have to eject a mass of stars roughly equal to their own combined mass.
Wait, say that again?
They eject a mass of stars between about 0.5 to 4 times their own mass.
So if the two black holes together weigh 104 million suns, they could kick out 400 million suns worth of stars. Easily? From the very center of the galaxy. That has to leave a mark. It leaves a scar. A massive one. We call it core scouring.
Core scouring. It sounds like scooping ice cream out of the tub. That is exactly what it is. The binary black hole is the scoop, and the dense central star cluster is the ice cream. It just scoops out the center of the galaxy. If you look at a typical spiral galaxy like ours, the center is bright. It gets brighter and brighter all the way to a sharp peak in the middle, a cusp.
Right.
But if you look at a giant elliptical galaxy, the kind formed by these mergers, often the center is flat. It has a low-density core. It's missing light.
The mass deficit. That's the stars that got kicked out.
Yes. That flat core is the footprint of a past binary black hole. It's the crime scene. The stars that should be there have been flung out to the suburbs of the galaxy, or even ejected entirely.
That is incredible.
Yeah.
So when we look at a galaxy like M87, this giant elliptical, and we see that flat core, we're looking at the empty dance floor where the black holes cleared the room.
Exactly. And this connects directly to the M-sigma relation.
Oh, right. The M-sigma.
Yeah.
This is the tight correlation between the black hole mass, M, and the galaxy's velocity dispersion, sigma, right?
Correct. It's one of the tightest, most fundamental correlations in all of astronomy. Big galaxies have big black holes. Small galaxies have small ones. The fact that this relation is so tight suggests that the black holes and the galaxies grow together. They co-evolve.
And this merger process is how they do it.
It's a key part of it. The process of core scouring and merger evolution helps regulate this relationship. The black hole isn't just a parasite sitting in the middle, it's a sculptor. It shapes the galaxy that hosts it.
It shapes the galaxy by throwing parts of it away.
Construction through demolition.
I like that. Okay, so we solved the final parsec problem. The triaxial shape feeds the binary stars. The binary shrinks, it scours the core. Now we're at the finish line. Phase 3.
Phase 3, the gravitational wave regime.
The black holes are now how close?
We are talking milliparsecs, a fraction of a light year, maybe the size of our solar system or even less. At this point, the stellar slingshot becomes inefficient.
And this is where Einstein takes the wheel.
Yes. Up until now, Newton's gravity was mostly driving the bus. But when massive objects get this close and move this fast, they violently shake the fabric of space-time itself. They emit gravitational waves.
And this emission costs them energy.
Huge amounts of energy. And unlike the stellar slingshot, which relies on the luck of a star wandering by, gravitational wave emission is constant and unforgiving. It drains the orbit relentlessly. The black holes spiral in faster and faster and faster.
This is the famous chirp.
The chirp. The frequency of the waves goes up and the amplitude goes up. Whoop, 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 W, whoop, whoop, double, whoop, until... Well, a new, bigger, spinning black hole is formed. It rings down like a struck bell, and then space stops shaking, at least locally.
Now, you mentioned in the notes that this is relevant to something called LISA. We all know LIGO. LIGO found gravitational waves a few years ago. Why do we need a new detector, LISA?
LIGO is an amazing machine, but it is ground-based. Its arms are a few kilometers long. That means it can only hear high-frequency gravitational waves, the final screaming moments of merging small black holes, like 30 or 60 times the mass of the sun.
Stellar mass black hole.
Right, but the monsters we are talking about, the supermassive black holes, they are millions or billions of times more massive. They are too big. Their chirp is a low, deep rumble. The frequency is too low for LIGO to hear. The waves themselves are millions of kilometers long.
So they would just wash over the Earth without LIGO even noticing.
Exactly. So we need a bigger ear.
We need an ear in space.
That's LISA, the Laser Interferometer Space Antenna. It'll be 3 spacecraft flying in a triangular formation, millions of kilometers apart, constantly firing lasers at each other to measure their exact separation. It will be able to detect these low-frequency rumbles from across the universe.
And based on Kahn's work, LISA should be very busy.
That is the key implication. If the final parsec problem was real, if black holes stalled out, LISA would hear almost nothing. It wouldn't find any supermassive mergers. But Kahn's simulations suggest these mergers are prompt. They happen efficiently. That means the universe should be humming with these events. LISA should be able to look back in time and hear the entire history of galaxy formation written in the language of gravitational waves.
That is a beautiful thought. We are building a machine to listen to the growth spurts of the universe.
It really validates the whole field of numerical simulations. We simulate it on a computer, predict the hum, and then build a multi-billion-dollar detector to go hear it. It's the pinnacle of the scientific method.
So let's bring it all back home to Milkomeda. We've established the black holes will merge. The galaxy will become a giant football-shaped blob. The core will be scoured out. What about us? What about the solar system?
As we mentioned, we probably won't be physically smashed, but our address will change.
We're moving to the suburbs.
Or the boonies. Simulations suggest there's a roughly 50% chance the solar system will be swept out to an orbit that is 3 times farther from the galactic core than we are now. We'll be way out in the stellar halo.
A room with a view.
A great view of the new Milkomeda galaxy. But there is also a roughly 12% chance we get ejected entirely.
Cast adrift. Like completely unbound.
Just floating in intergalactic space. The night sky would be perfectly black except for the faint, fuzzy glow of Milkomeda receding in the distance.
That is simultaneously terrifying and peaceful to think about. But practically speaking, the sun will have expanded into a red giant by then anyway, so Earth is toast, regardless of where we live.
Yes, the view is strictly for our robotic descendants or whatever cockroaches managed to survive the red giant phase.
Long live the cockroaches.
Indeed.
So to wrap this up, we started with a famous collision. We zoomed into the center to find a deep theoretical crisis, the stalling black holes. We solved it with geometry, the messy triaxial shape of the galaxy acting as a conveyor belt for stars. And we ended with the grand chirp of gravitational waves, a sound we are building a new ear to hear.
It's a story that tells us that imperfection is necessary. If galaxies were perfect spheres, black holes would never merge. The universe would be static. It's the interactions, the messiness, the breaking of symmetry that allows things to grow and evolve.
And I think that's a perfect place to leave it. The final parsec isn't a barrier. It's just a toll booth, and the price of admission is a few 100 million stars.
A small price to pay for a new, bigger galaxy.
Thanks for diving deep with us today.
My pleasure. It was fun.
And here is a final thought for you to chew on. If these mergers are so efficient, and if every giant galaxy we see, like M87 or Andromeda itself, has undergone them multiple times, that means the black holes in the center of those galaxies, there are actually graveyards. They're the combined remnants of dozens, maybe hundreds of smaller black holes from the beginning of time. When you look at a supermassive black hole, you aren't looking at one object that just grew fat. You are looking at a family tree.
A family tree where everyone ate each other to get to the top.
Exactly. Until next time.